Добрый день. Hello.
Добрый день.
We're still too early.
Yeah, I can hear you.
So it's impolite to be in a party too early.
I never look at the first 45 minutes.
By the way, when Zoom, it's possible to stream directly on YouTube. Then you don't have to move around the files.
But you know, maybe you decided then to cut off the beginning or the end
Okay.
or something in the middle.
Yeah.
And some participants could be scared if it is streamed immediately to YouTube.
Yeah, I understand this. Actually I am scared. It's a good way to have less stupid comments. By putting it on YouTube, people are a bit more careful, I think.
Hi, Andres. And just in case, can you share something here just to check that it works?
Yes, I can. Should I try?
Yeah, I mean, Andres, who is the speaker.
Sorry.
I joined with my iPad. It's the second, Andres. So if you can give access so I can share from there.
But you can just share. I think everybody is allowed to share. God.
It's not clear what you're saying. Sasha, we don't hear you.
Sasha is not saying anything, I guess. He is muted.
Yeah, but now we see also the share of not only of the screen but also of the
Nice. And right
speaker. Good. Yeah. Hello. Should we wait for Vereshchagin? I guess. Does anyone know that he is not able to come?
I don't know. Maybe just let's wait a few minutes, maybe.
Yeah, but then using this few minutes, you may present the speaker and explain what he will tell us and all of this.
Well, I think the idea was to
Give a talk.
Sorry?
To give a talk, yeah, but what will we talk
to give
about?
a talk on, and you know, I'm not as well quite familiar with that, so maybe it's better for Andres to tell what he's going to talk about. So, but...
yeah, if you give me, I can start whenever you want. So
no, you can start slowly. Maybe if Vereshchagin comes in a few minutes or somebody else comes in a few minutes, we can repeat the technical part.
I can give a brief introduction of like the high level.
What is monoculture social welfare? It's a bit frightening. So just tell us something.
So I think this comes from this idea of algorithmic decision making. So I come from computer science department, especially a lot of apply AI from one hand, and the other one is more theoretical and game theory. And recently, because there's a lot of kind of systems using data-driven decision making, for example, in domains such as banking, recruiting, even in the US, they use it for predicting the probability of recommitting a crime. So there is a lot of attention in how fair these kind of algorithms are. And so like a really nice example is actually used. So the courts of the US use a tool. It was called Compass. So it was basically a measure of risk that a person has to recommit another crime. And when they analyze it through data, it turns out that there was a bias towards some people. So in particular, basically the positive rate. Sorry, the false positive rate.
Based on what? It would, of course, it would be nice to know whether somebody will make a crime, but just looking on the face or what do they use as input?
That's a good question. So I'm not familiar by specific, but they use from all the history of the person. How many actually the data is available, so some students have played, so how many crimes they have committed, education, economic profiling, what the crime was, where they live, or basically any demographic filters they can find. And the key, what they found is that Afro-American offenders, the precision of the algorithm was worse, the accuracy for Afro-Americans than for white or Caucasian offenders. So that was kind of the main finding, that there was bias towards some specific minority groups. And I think this was where basically fairness in AI, which is like the high level topic, came attention and is becoming a very prolific and productive kind of research, specifically focus on when systems are going to be deployed in society and understanding all the impacts they have and so forth.
Okay. Okay. Okay, let's probably, Svirishayin is not here, so let's try to start the mathematical part, and if he can make later hear the recording. Yeah.
So I'll start with this paper. I don't know if you're familiar, John Kleinberg. When I started computer science, I read his algorithmic book, and now he's also kind of doing a lot of work with economists on this idea of kind of understanding the impact of algorithms in society. And so the framework I'm going to show today is quite relevant. He was thinking on this following kind of future is, imagine you have an algorithm that can help you recruit people. I don't know, postdocs, professors, whatever. And you have several universities, all of them want the best applicants. So imagine you have two firms or two universities, and they have to decide whether they can use the algorithmic ranking. Let's say that's kind of a software you buy, or they can choose to rank by themselves, basically just a human curator list. The trick here is that the algorithmic ranking is going to be the same. It's going to come from the same distribution for everybody. So the setting here, the idea is firm 1 can choose whether to have their own ranking or the shared algorithmic ranking, and the same for firm 2. So the question that the authors ask is whether, and the second assumption is that the algorithmic ranking is going to perform better than a human ranking, But the question is whether if choosing both firms, the algorithmic ranking can decrease the social welfare. And that's why they call this kind of idea of monoculture that comes from agriculture. The question is whether, even if there is an algorithmic solution that performs better than any other human solution, what happens when everybody is homogeneous and uses the same solution?
No, I am lost. So, but in your example, universal, imagine if A is the best candidate according to algorithmic ranking. Anyway, he can or she cannot be recruited in both universities.
Exactly. So
but why then following the algorithmic ranking? No, there is a question where I wants to go, but what you mean saying that algorithmic ranking is worse? How you say that using the same algorithmic ranking in two companies is worse, but you cannot use the same. You need to let the people choose.
Yeah. The game is as follows. So if both are using the same algorithmic ranking, so it takes places. So first, imagine firm 1 starts, so they choose the top one, A. Now A is gone, and then firm 2 has to choose. And clearly they're gonna choose the top that is available, so they're gonna choose C, and then firm 1 go. So they play one-on-one. So another option would be, for example, oops, sorry. Wait. Another option would be, for example, that firm 1 chooses their own algorithmic ranking, and firm 2 the algorithmic ranking. So in this case, firm 1 starts with B, which is gone, and then firm 2 now can actually grasp their top by the ranking. So the idea is the question is when they both are using the same ranking, what can be, if they can be worse or not. So I'm gonna go a little bit in the math, and basically the whole paper is show what are the conditions of the ranking that entail that choosing the same ranking is worse than choosing a different ranking, even when individually is best. So maybe if I go deeper, it's gonna be more clear. So the idea is as follows. What is a ranking? The idea, how do we model the ranking? Is that there are n candidates, and they have intrinsic values. And there's a lot of assumptions. The big assumption is that the intrinsic values is the same for every employer. So basically, if you choose, employer, you choose candidate I, is gonna give you an utility xi. So the idea is rank them as best as possible for you. And of course, the idea is that you're gonna draw permutations from some distribution.
Yeah, okay. Okay.
And the nice kind of modeling is how do we define these kind of ranking permutations. The main part here is that we are gonna choose a random mechanism over the permutations R. So first, the game is as I told you. So there is a random order in which each firm hires the highest rank remaining candidate according to the ranking. So each of them chooses a ranking and then go playing and choose the top one. And then the assumption is that candidates, of course, automatically accept the offer from the firm. And now goes the kind of the probabilistic part. Is the idea is we assume there is a family of noisy permutations. So this one here, we call it f of theta, and theta is gonna be this parameter that is gonna give us an idea of the accuracy or noisy of the permutation. So bigger theta means the ranking is better, and lower theta, the ranking is less accurate, more noisy. So
let me check that I understand correctly. So there is some true ranking, which means that there is a sequence of values, and each candidate has a cost or I don't know, a price or value or I don't know what, and they are fixed and they are the same for all employers.
Yes, yes.
But then there is some randomized permutation. And then when we apply this ranking to a true sequence of candidates, we get some randomized permutation.
Exactly.
And this can be done differently by two firms, or you can use the same permutation for both of them. And all these three permutations are taken from the same family.
And yeah, and one more thing is that, so we assume that, so humans basically can create their own ranking with a parameter theta h, and the algorithm has an accuracy theta a.
So they are different. So they taken, human evaluators take from the other distribution of permutation.
And the
then
whole thing is that the algorithm has a better accuracy, or it's less noisy.
Yeah, it's not clear what we do not define what is better, but at least it has some different permutation. And then after the permutation is chosen, then the firm in random order or they alternate these two firms. I don't understand.
They alternate, yeah.
They alternate,
in their top
and they taking the first available candidate according to their rank. And at the end, they have n over 2 candidates each chosen according to this rank. So they may either use the common list or two different lists, and the common list has better accuracy.
Yeah. So what it's not a common list, it's a common, so it's basically they generate, it's a random mechanism. So even though both can choose the algorithm, still is on expectation is the same. But it is, the whole idea is
so the common list is produced by applying a random permutation from this common permutation family.
A common distribution, yeah.
And also each local ranking are also performed by a random by independent random permutations from some other distribution, and they are this is different distribution. In some sense, it's less accurate. That's what you are saying, yeah?
Yes, yeah.
But as I understood correctly, so like when we use, if even they use a common distribution, but two firms might get different lists, right?
They independently take a random element from permutation from the distribution, no?
Yeah,
yeah,
exactly.
But they just sample independently these two, but from the same permutation from the same distribution, but the permutations itself might be different.
Yeah, exactly. The realization can be different. So
Yeah. If you take two independent random values of the same random variable, then they will probably different. Yeah. Good.
And the detail of what they define as basically a noisy permutation family is the following. So they have three kind of conditions. The one that they use basically only for the proof is the differentiability over the of this parameter theta. So they say basically what is a permutation family is a distribution over the possible permutations.
So this permutation doesn't take into account excess, or it takes into account excess.
Not for the it doesn't. So it's we only think of these as permutations. Of course, it accounts. So the second point is the optimality. So the idea is we want that the optimal ranking.
No, just explain where it's defined, the random distribution on f theta is mathematically what?
Yeah, so
for every theta, the simple thing is for every theta, we have a family of permutation on the set of n elements. But if you then it doesn't depend on the values of candidates. But if it depends on values of candidates, then it's something more complicated. Just tell us what it is.
Yeah. So okay. So first, we forget about theta in the first one. The first one is, so you have a probability for each permutations over the n candidates. Now, when they put theta is on the second two definitions. The first one is the optimality. So they say as theta grows, the bigger theta, they say the more probable that you get the optimal ranking. And what is the optimal ranking? Is the one basically that is ordered by their intrinsic valuations. So,
Okay.
so that's where they put these two things together. And this third one is the monotonicity. And the idea is here that, so if you have a ranking and you remove, okay, so some notation, the expectation here of a ranking is actually the value, the intrinsic value, the xi.
Yeah, so this boldface X is the set of true values.
Yes.
Yeah. Yeah.
So the idea here is that the optimality, so the theta serves as an accuracy parameter. For large theta, the noisy ranking converges to the true ranking over candidates.
Yeah.
And the third point, the monotonicity condition, states that a higher value of theta leads to a better first choice, even if some candidates are removed after ranking.
This is not clear. This permutation depends on what? Just mathematically, it can be applied to any sequence of n elements, or to any sequence of at most elements, or what happens?
Sasha,
So I think we just have we fix the values, and then we just consider distributions over n elements. So let's say a distribution where just always outputs the correct order is very good, but I think the assumption is that we
we
can't
look at p minus s is somehow produced on some subset of s of x. So pi is defined on something more complicated.
Sasha,
Yeah.
I think that in this definition, X is just a set, just a finite set, and that's it.
So permutation family is just for every theta, we have a random variable which for every theta and for every sequence of x's of any size, we have some distribution on permutations over x's. Yeah.
X is fixed, as I understand in this definition. Just
but
fixed
then p minus s applied is not to x. In third definition, there is something which is pi with superscript minus s.
Right. So we consider that permutation pi. Then we remove from the permutation all entries from s. We obtain a permutation, I mean, just a sequence of candidates, sequence of elements. And we consider the first one in that sequence, which actually doesn't depend, as I understand, from, it might depend on S, because if you remove the first candidate, then pi 1 minus S becomes another candidate, the first candidate outside.
Yeah. So pi is just permutation of all, but permutation, this depends on the values, or it's just a distribution depends on the values, or it's distribution of the permutations independent of the values.
Sasha, what are values?
X1, xn.
X1, xn is just a finite set. Just say 1, 2.
It's fixed forever, yeah?
In this definition, it's fixed.
Yeah.
Yeah,
So
okay.
the way I would say is, imagine there are two thetas, theta 1 and theta 2. The idea is if you fix one theta and it creates a distribution. So you have now two family of distributions, and the whole thing is if theta 1 is better than theta 2, then the probability that the true ranking is optimal is higher for the bigger theta. And the second one, imagine if you take the first item of ranking produced by theta 1 and compare it with the value of the first candidate from theta 2, then in expectation, the first candidate is going to be better than the first one from the other one.
Yeah. So we have X is fixed completely forever, and there is a distribution on permutation, a family of distributions of random distribution permutation depending on theta, and it has this property. Okay.
Good.
Yeah.
So what comes next? Okay, so before I go, the whole idea is okay. The main theorem then, the idea is that they put as an objective function is what is normally used in game theory is called the social welfare, and that is the sum of the utility of all employers.
Yeah, sorry, I forgot. So permutation family as f theta is I remember, and what is distribution D is just x1 xn or what? This theorem one is what?
Yeah, this theorem. Let me explain it. So it's as follows. So imagine now we have the utility of the first player of the first film choosing a strategy, for example, the algorithmic ranking. Let's call it like that. In fact, they use S1. So the utility of the first player choosing a strategy S1, and S1 basically can be.
But you say that both firms have the same for the people have the same values for both firms, yeah? Or now it's not the case.
Can choose they choose basically if they want to use the algorithmic ranking or the human ranking. So imagine if there are two turns. So firm one first chooses either algorithmic or the human ranking, and then the second player, now given that the first one chose S1, they have to basically choose again, they have to choose their strategy. So
yeah,
the main idea here is given we first know that the algorithmic ranking is better than the human ranking. This is because we are going to assume that theta A is bigger than theta human. So if you're the first player, you always are going to choose the algorithmic ranking. That's your optimal choice. You are going to assume there's only two for the rest of the paper. There's only two turns. So first player and second player, and then it's over.
Yeah.
But will you agree that, of course, if you're the first player, you choose the best ranking?
Yeah.
Now, okay, so now what happens next? The second player now is faced that given that the first player choose the algorithmic ranking, they can now decide whether they use the algorithmic ranking or they can use the human one. And again, because it's already basically fixed, you can also assume that the best you can do if you are the second ranking in the second player, and it basically in the first stage there was a user remove. So now the best idea is also to choose the best ranking possible, and it's the algorithmic ranking. So the first kind of idea is that if both players are strategically and they want to optimize their utility, they should choose the algorithmic ranking.
So dominant strategy is that whatever strategy uses the other player, algorithmic or human, for the first player, it's better to use that strategy. That's a dominant strategy, yeah?
Yeah. So this is basically if you are selfish and you only want to optimize your own utility, each firm will choose the algorithmic ranking.
Yeah.
Okay, so the theorem then is as follows. So they also say, okay, so
But what is social welfare?
Yeah, that's what I'm going to find now. So the social welfare, it's basically the sum of the utility. So in the equilibrium point where both chooses the algorithmic one is the utility of firm one that chose the algorithmic plus the utility of the second one. That would be the social welfare of this equilibrium. And the theorem says that in the equilibrium where both well, it's not equilibrium, in the point where both chose the human
Yeah.
algorithmic, then you have this basically utility, and the theorem says that, well, we're going to derive the conditions such that choosing the human is better than the algorithmic solution, even though the second one, the algorithmic solution, is the equilibrium point. So this is basically what we want to prove.
So the theorem says that such cases are possible, or that
Even
they
though-
happen always, or what?
No, it's possible. So it's possible that it is strategically. So what was it is a strategically strictly dominant strategy. So this condition, and it's also possible that this happens, and we are going to actually aggregate two conditions for the distributions that show when this happened. So we are going to derive the conditions for this to happen on the family of distributions.
Does it mean that should it sound like a kind of paradox that there exist examples such that in one sense these two methods are related in one direction, and the other sense that they're related in the opposite direction, and this is not what we should expect intuitively?
Exactly. In fact, the authors basically say our main result is a pair of intuitive conditions under which a Bryce paradox style result occurs. So in the same
But
words.
I wouldn't say it's a paradox, because we have some algorithmic and human is some nonsense. There are just two ways of evaluating the candidates. In one case, we use this evaluate them once and use this evaluation to choose two best candidates. Actually, what if I understand correctly, we take an algorithmic ordering and we take two best candidates. Yes.
Yeah. So the paradox is that
In
choosing
the other
the
case, we have two independent evaluations and take the best candidates from each evaluation.
Yes.
And we say that using two different evaluations can be better than using the same evaluation twice. And it's quite possible. For example, imagine that the method of evaluation more or less reasonably selects one of two best candidates, and so internally the evaluation methods makes just two candidates, finds two best candidates, put them in random order, and put the rest in the random order. Then, if we use no, it's another direction. No. Sorry. I cannot say the example, but it seems that just running twice the evaluation procedure generally can give more information than running it once and using only one result from this procedure. Somehow. But maybe let me make another attempt. So imagine that the random procedure puts on the first place one of the evaluation puts on the first place one of the two best candidates, and other places are randomly permuted. So if we use it twice, there is some reasonable chance that we get two best candidates. And if we use the procedures once and use only the combined only one list, then the second candidates will be nonsense. And we will not, very small probability, get two best candidates. So somehow using the algorithm twice is better than once. That's what is happening, yeah, or not?
So I don't know what's running once or twice, because it's a ranking. So it's basically you fix the ranking.
No. But when you say human, you take two independent
Yes.
ranking by two different
From the same
firms.
distribution. Yeah.
And if you and you compare it with what happens if you use one ranking and both firms use the same ranking.
No, it's they use a different ranking, so they it's like they produce two rankings, but from the same distribution. So at the end, there's no.
They produce two rankings from the same, but you say there is one algorithmic ranking. It's kind of confusing then.
Yeah, sorry.
There are actually two algorithmic rankings.
Yeah. So they basically it's like imagine. Yeah, because the algorithmic ranking is basically random. Each of them has a realization of the algorithmic ranking, but it's not actually the same. So
somehow the parameter is better, but using it, and so we have two ways of ranking, and each of them, one of them is better when
so
better accuracy in some definition, and then is optimal when we use it against other, and still if we take the sum, things are different. Okay,
exactly,
so it's a different thing, yeah.
So the dilemma or the paradox is that individually choosing the algorithmic ranking is better, but taken together, you're worse. So and that's the Bryce paradox. I think it's like that is when you in community times, like everybody individually prefers to go through path A instead of B, but if you take it together, basically using the other path would be better for everybody. And also here the ranking, think of it like, I don't know, using Google Scholar, that's the algorithmic ranking. Maybe two people can search for the same keywords but get different results. So the idea here is if everybody is using Google Scholar instead of using their own, I don't know, library, maybe we're losing something in social welfare. And okay, so what's
like the prisoner's dilemma or what?
It has that kind of flavor, yeah. So I'll show now there are two conditions basically that over the permutations that will conclude the results. And the definition, the first kind of condition is the following. They call the preference for the first position. I don't like much the way they frame it, but if you read here, the second paragraph is very kind of clear what they wanna kind of say, and they say the idea is that if you have two permutations from the same, basically two realizations from the same algorithm, so you pick from the same theta two rankings, in this case pi and sigma, so they both come from
independently.
Independently, but from the same distribution.
Yeah.
Here, okay, so they come from the same distribution, that's important. Then they say, suppose we draw two permutations independently, and we compare basically the first rank candidates, and the first rank candidates differ. So there's some noise and they differ. And the important thing then, the expected value of the first rank candidate in pi is strictly greater than the expected value of the second rank candidate.
In which pi? In pi, the pi and sigma, yeah.
Yeah, I could change. So the idea is, in expectation, the first rank is always better, strictly better. That's kind of.
What is the role of sigma then?
Yeah. So let me. Okay. So.
What is the role of sigma then? I don't understand.
I'll show you. So
you can ask that the expected value of the first ranking candidate is greater than expected value of the second ranking candidate without any sigma. Yeah. This is assumed or not?
they say it's so you choose two rankings. Okay, I'll give intuition here. So the idea is you have first the ranking pi. So imagine you have it's gonna pi 1, pi 2, that comes from theta, and then you have a second ranking sigma, which also comes from theta, sigma 1, sigma 2. Okay. So the algorithm says if sigma 1, is different than sigma 2. Sorry, no.
Okay, but without sigma, there is a simple condition that the expectation of the first candidate is better than the expectation of the second candidate, which is a property
Yes.
of the permutation. So we assume this or not?
So let me it actually is not trivial to get that. Well, it is. So it's here. By definition, you get the greater or equal. Okay, so we are gonna basically make it.
No. Here we have two different. We have theta prime and theta. It doesn't say anything about.
Exactly. So
if we take first and second candidate, it's just we would compare with different s. It's not
yeah.
So it's a different condition.
From the definition, it's not trivial to get that the first one is better than the second one. So
Sasha,
yeah.
Sasha, these are quite different properties. So it's naturally to assume that without any condition, the expectation is non-negative, right? But we assume that it is strictly positive under that condition. And the condition here, I think it's very important. Because you see...
No, but it's completely different things. It's just value of the first and the second ranked candidate. It's not considered before. Before we considered different values of theta. And now we consider only one value of theta. There's something different.
Right. I do not claim that something of this kind follows from the previous definition.
Yeah.
I
Exactly.
understand why we need some condition here, because it might happen actually that all the candidates are the same in a sense. And then the expectation...
No, but we assume that all x's are different, I guess, no?
Where we assume that?
Sorry,
okay.
By the way, I do not see from which condition it follows that the condition there has positive probability. Actually, it might happen that the condition in that property has zero probability, right?
Yeah, and I mean the only thing where we could kind of get something is the second definition of optimality, but that's for big theta, not for any theta. So in fact, that's the whole thing. For a noisy, if theta is very low, it's a noisy ranking, and it could happen that there's no definition here about the order. So basically, it could be anything in expectation.
Okay, let's see what is going later, because now it's somehow confusing, but maybe at least some flavor what is happening.
The whole thing here is that if you increase theta, the ranking becomes better, okay? But it doesn't say anything about how good our ranking is. So that's where kind of this definition comes. So they impose a little bit more about for a fixed theta, what you can that basically the first one is better than the second one in expectation. So for the first time they put some characteristics of the family of the rankings for a fixed theta. All the other definitions were to compare different distributions. Okay, so the idea is okay, why they frame like this? So imagine now you have two firms, they both get a ranking from the same distributions. So we have basically two rankings, theta and sigma. And here the idea is, if you choose, let's see, if you choose to get imagine you are the second player, and basically if player, oh, I'm not writing, wait, here. Over here. So if the first player chooses to take the candidate from sigma, and the second one as well, then because the first player is gonna take sigma 1, then the second
Sorry,
player
I'm lost. You are explaining what now exactly?
I'm gonna explain and give some intuition on. So they say that this condition that they impose is equivalent to this. So
yeah,
I think the intuition on the right is way better, and that's what we're gonna use, and it's equivalent to basically the definition they put. So I'm gonna basically show this.
yeah.
And I think it's gonna make clearer also what is the intuition of this definition. So the idea here is that assume now that we can call, for example, this by ranking A. It's not writing. No. We can call this A, and this can be H. So, okay, so here wait, I'm gonna do it the other way around. I'm gonna call this H and this A. So what happens if the second player, both players choose the second ranking? Now, what is the candidate of the second player? Well, because the first one is gonna choose sigma 1, then the second player is has to get sigma 2. I'm used, so that's basically this one. And now, what is this? This would be the first player. Oh, it was AH, okay. In this case, the first player again takes sigma 1, but now the second player is gonna take what is gonna take? Now he goes to his ranking, which is H and or pi, and he's gonna take the first one if and only if it's not so it's gonna take P1, but only if it's different to sigma 1, yeah, if they're different candidates. So basically only if pi 1 is not sigma 1. Yeah, because if they're same, then this candidate already was removed, so then they go to the second one. So basically, and then they have to, or they take the second candidate if I have no space, if they're the same. Sorry, the notation. So the idea is he's gonna get the first candidate that he wants only if it's different to the sigma 1, or he's gonna take the second one. So the whole idea here is that, notice that in expectation, because they're from the same distribution, the rankings, the sigma 1 and pi 1 should be the same. Yes? But
No, I'm completely lost. Just try to look at also at the paper which you sent. And
okay.
On the second page of the paper, they say exactly what they say. However, while the human evaluator produces a ranking independent of any other firm, the algorithmically generated ranking is identical for all firms who choose to use it. So this is different. They don't understand then whether they use just the different method of evaluation twice, or they use another method once and use it. This is what confuses me.
So oh, sorry.
So again, the question. So every company can use its own evaluator taking from some distribution, or they can take an algorithmic ranking produced by some other distribution. The question is whether we use two independent samples from algorithmic ranking, or we make only one sample of algorithmic ranking and use it for both companies.
I think it's two independent samplings.
But then it seems that it's not what they say on page 2 of the paper. So there in the second column there is
I think it's a valid question. Maybe it's easy to finish the theorem. Maybe we can discuss it.
Okay. Let's okay. Just say what you want to say, and then we'll see.
Yeah. Okay. So the intuition here is the following: is that if you choose, given that the first player chose ranking A, if you choose again ranking A, then you're gonna get sigma 2 proliferate 1. But if you go to the other kind of independent distribution, then with some chance you get your first candidate by 1. Yeah, and with some chance you get by 2. And the whole idea that is in expectation, pi 1 equals sigma 1, and in expectation pi 2 equals sigma 2. So I think you can see then that you're always going to be better choosing the independent ranking, because you have a higher chance to get your first candidate. So that's kind of the lemma 1 that we're going to use. So they say that condition 2 derives this lemma, and basically they say is the second firm always prefers to use an independent ranking mechanism from its competitor. And that the whole thing is that you have a higher probability of because of the noise of getting your first candidate.
Yeah. Okay.
So now, actually the theorem, we can use the lemma to show. So the theorem now says, what does it say? It says basically, suppose that we have a candidate family that satisfies condition 2, and also condition 3 that I'm gonna just show in a second. So, okay, so if we have a family of distributions with condition 2 and 3, and the algorithmic ranking is less noisy than the human ranking, such that it is the strategic dominant for both firms, even in that case, the social welfare is going to be worse if they use human evaluators. That's basically the idea I show here. So even though individually they prefer the algorithmic, socially is worse off. And the second kind of, the third condition is this one, which is actually really nice. They call it preference for weaker condition, and it reads as follows. So I like maybe the intuition. The idea is that when a random candidate is removed from a list, the remaining candidate is better in expectation when the randomly removed candidate is chosen based on a noisy ranking. So okay, so the idea is as follows: is if you have here it gets a little messy. So you have one ranking from theta 1 and 2 rankings from theta 2. So here, and this is important. So theta 1 is better. So the idea is, if now you have, we're going to fix this ranking pi, we come from a worse distribution. So the idea is, and we are going to remove. So if from the, let's say the bad list, we remove an element, remember sigma is from the best list. So if we remove a better element in expectation, then so you have a bad ranking and a better ranking. We pick the first candidate from the best ranking and remove it from the bad ranking. This is what we're going here. So basically, we're removing a good candidate. So the value is going to decrease more. Hence, but if we have the same ranking and we remove the first one, but from a worse ranking, of course, in expectation, we're going to remove a worse candidate. So the idea is it's better to remove a worse ranking than removing like a good potential candidate. That's all that they're saying. So hopefully that's clear.
Okay, so they say that the second ranking still somehow improves has better chances to provide a good candidate than random choice, something like this, yeah?
No, it's the same ranking pi, but it's better if you remove someone from a. If you take now you have one fixed ranking pi, and then you have two other rankings, theta from a bad ranking and sigma from a good one. So and then they say pick the first candidate from sigma and remove it from pi, and that's gonna make it worse than if you remove the first one from the same list, which makes sense because in expectation you would expect that basically that this you would expect that because the tau ranking is worse, in expectation the candidate is worse. So it makes sense that removing a worse candidate from a list makes the list better.
Okay, so this is a requirement for theorem one, or it's some other theorem.
Yeah, exactly. So these two conditions are on the kind of the internal rankings. So definition 3 and the other one that we discussed are necessary for basically for the theorem. So which we are ready kind of to show. So remember, we want to derive this result starting from this. So okay, let's do that here. 1 second. Okay, so by the lemma, okay, lemma 1 give us this idea that with the same kind of accuracy, you got the second. You want this independent kind of mechanism. So let me write it here. So lemma 1
it's independent mechanism. This UAA means that we take two different copies of A or one copy of A and use twice. This is we return to the same question, I think.
Here's two different copies. So in fact, because it actually says the whole idea is we prefer the second here. The second firm will choose an independent ranking.
No, prefer to choose an independent ranking to what? To choose the same ranking or to choose the independent ranking from the same distribution? This is the question.
Well, in this case, they're all the same distribution because the theta is fixed. They're the same, so the algorithmic.
But AA is using the same two different samples of distribution A, or they use the same sample. This is the question.
Okay, good question. Let me. Checking the proof. I think that using actually the same, yes, because so they assume here, like I said, that you get sigma 2 with priority 1. So they assume that the first player chose sigma 1. So yeah, here is the same exactly. Yeah. So there's some.
Okay, but imagine then we have only one distribution and use it both for human and for algorithm. So we can use two copies of the distribution, independent, twice measuring, or measure it once and use this list twice. Do they claim that under some conditions the first thing is better, using twice the distribution, not the same?
Yeah. So that's exactly what they're saying. So using twice is worse than creating a new independent. That's exactly this lemma.
And then in theorem, they say that even if we change a bit our distribution, this improvement in the distribution doesn't help. So it's the advantage of using better distribution if we use it twice is overweighted by the fact that we use it twice and get worse results, something like this, or not.
Yeah. So yeah, it's gonna go. It's actually really fast. So basically, lemma 1 give us this, and also
we
have basically. I don't know if I define this notation, but the idea is this is the utility derived if I choose algorithm A, and this is the accuracy of algorithm A, and this is the accuracy of the human, and so here, this is lemma 1.
No, theta is parameter.
Yeah. So here I'm using the same parameter. So for the meantime, and also the second equation is trivial. So if the algorithmic and the human algorithms have the same parameter, then of course the utility is the same.
Yeah.
So with these two, basically, we have that. What would we have? That the utility of choosing the algorithm on the first and on the second, it's lower than this. Okay, so with these two conditions, you get this inequality. Actually, they say it's strict. I have this pen. Sorry.
So maybe just because the inequality from lemma 1 is strict. I guess because there was a strict inequality on pi1 and pi2.
Sure, yeah, that's it. So we got strict everywhere. And notice that this is the social welfare of choosing the algorithmic solution. And here's where they use actually now. Okay, now what they do is they use the first definition of the of the rankings, and it's the differentiability over theta. So they say there has to be a theta for the algorithmic solution such that the utility of using the algorithmic ranking is bigger than of using the human ranking. Okay, so basically there must exist some theta, and such that not only the algorithmic ranking is better, but it's so bigger than, and this is kind of, they don't claim why it's true, but they say basically such that this happens. This pen here. So I'm gonna rewrite the same this inequality, but it's gonna change the sign. So they say with this theta that must exist, they don't explain why.
No, maybe just for continuity reason. If for the same value of theta we have a strict inequality in one direction, then probably if we change one of them a bit, then we still have the strict inequality, no?
Yeah. So what they say is basically that the sign will change. So from this equation to this, the sign basically change. So from stricter inequality now is a greater or equal. Okay, so they say there must exist some theta hat such that with that parameter, because this is gonna be big enough, the inequality is gonna change. They don't actually. I'm not convinced why this is always true, but well, this is kind of maybe the idea. So they say now we have a greater or equal, and because of the differentiability of theta, they also say if that is true, then there must exist another theta asterisk in this case, such that this basically condition now becomes an equality. That's because of the differentiability. If it goes greater or equal, then there must exist also for the equality. Oh. So basically they say you can also have this, but for another parameter. So basically, this is the main point, that there exists a parameter such that this holds. And now we're going to use the condition 3. So you already used the condition lemma 1, and we're going to use this condition, definition 3. And it's as follows. So here, first notice that the utility derived, so this. Okay, what is this? This basically means, given that the first candidate was taken from ranking, the algorithmic ranking, and the second one is the candidate from the human ranking, this means that what is the derived utility? It means that in expectation, you're going to assume this is human is the pi ranking and the algorithmic is the sigma ranking. So basically we are saying is he's going to take the first candidate from pi after removing the first candidate from sigma. So basically that's the derived utility, and we can also do the same here with the same parameters. So this is also now it's removing pi 1 after removing, so the second one chooses from pi, but after the list has removed also the first candidate in expectation. So notice here that actually if both choose human here, because it's an expectation, it doesn't matter in the proof if it's independent or not. So it's here. So basically, this is the expected utility derived from this. And notice that what was the condition here? The whole idea was here. Let me. So what was the condition? It's we need to see at this equality. So if we remove in the word, remember, it's better if we remove a worse candidate. So when we look at here, which one is, remember that the algorithmic one is better than the human one. So in this case, we will have that, where is the worst is pi. So we will have this kind of sense of the equality. So to finish, we can write basically what is the social utility of both firms choosing the human solution, that is basically the first one chooses the human and the second one. And we just basically show this inequality here. So we're gonna use it. So basically this is greater or equal. Here is the same, and we use the last inequality we just showed, which is this. And notice that basically this is what we had in this inequality. So the second, the right part of the equation, UH and UAH, we have it there. So we are going to copy this left part. So basically we have that, oh, this was here an A. By that part, we have that this is equals to UA plus UAA. And this, by definition, is the social welfare of choosing the algorithmic solution. So basically that give us what we wanted, that basically the social welfare of both using the human frame is greater or equal than using the algorithmic solution. That's kind of the main solution. They say in the paper that they also can show a strict inequality for some specific cases, but this is kind of the gist of the theorem. And then they do some kind of computational, they actually instantiate some models and show via simulations how much, they don't quantify how much the loss is. So they do that with simulation, but basically that is the main idea.
Yeah, but no, this is somehow several things mixed. So entire philosophical social speculation is completely nonsense, because there is nothing in algorithmic or human. It's just distracting names. Just the reason is whether we use one strategy or other strategy, one evaluation or use twice evaluations.
You can even say it's worse. They kind of use the social issues related language by missing the real social issue. But like they are proving, strictly speaking, that avoiding monopolization and running evaluation independently has some value. And it doesn't matter how exactly we are doing it in the result provided, but the question about monopolization
there are somehow two different questions. One is the effect of making the two experiments, two measurements instead of one measurement, and then you can study this effect without changing the distribution. You just have the same distribution, and you have something happening. You can compare something, and then there is an effect of change of distribution, and this is what I don't understand. So it may happen that what they do, they show that for reasonable values of evaluation, evaluating things twice is better than socially better than using the same evaluation, but still but this is one thing, and another thing, this effect is stable even if we use for the same evaluation, use some better evaluation or something like this. So there are some things which are mixed somehow, and it's interesting to understand what are the how it should be split into. So whether there, for example, whether there is some non-trivial result for using the same evaluation twice, or using once it. Do they claim that under some conditions using independent evaluation from the same distribution is better? And what is exactly this condition? Because
but I think the problem is also, if I understood correctly, that if we that also is interesting. If you use twice better evaluation, it can be worse than using a worse evaluation twice as well. I think that's the point.
Yeah, in
right?
a way, the worse is
Because
more.
of this condition.
Oh, Sasha, say it again. I'm lost.
If I understood, well, I think the point is also that using, twice a better evaluation is also might be worse than using twice a worse evaluation, because we remove
Twice, you mean the
better.
same evaluation twice?
No, two independent, no, because we can remove. So we choose first, the first firm chooses a better candidate, and then after removing it, a better evaluation might become worse then.
No, you mean that better. No, so imagine the correct evaluation, and other is some randomization with some small probability. Then of course it's better to use the better evaluation twice, because we get the two best candidates, and with this is the maximal we can achieve. And if we use randomization, we use something worse. No, what I'm saying is obvious. Probably you meant something else.
I guess the question is, can we build the two distributions such that we get a prisoner's dilemma or on these two distributions, that even assuming that the two players sample independently, each of them is incentivized to use the first one, but the Nash equilibrium is worse than both using the second one.
And even
did I understand correctly, Sashka Zachinsky?
Yeah. I mean, I thought that this was more or less theorem free. Maybe I'm misunderstood something.
Yeah, okay. So I know at some point we had a very good tradition started by Sasha Kazachinsky, that after the talk he sends some paper, short note explaining what was exactly in the talk. And this maybe this tradition should be continued, because I am now lost a bit.
Sasha, do you mean that you want to do this for the today's talk?
I mean, it's a tradition.
I know the tradition is just linked to quite personal. No. Once I sent a review for Laranto, but this is somehow this is somehow confusing, or I don't know. Maybe someone who has an experience in game theory, like Daniel Musatov or Misha Raskin, can explain what is to dummies what is happening, because dummies like me are completely confused now after all this. No, it's kind of, if we just forget about this social blah blah nonsense, maybe there is something interesting mathematical thing, but it's important to understand better.
What I get is that basically you're exploring a space for an optimal solution, and even though you can get a better ranking, but with less noise, you are way better with more noise to explore the environment, I guess. I think that's for me.
So better is using better. No, somehow if you make two measurements, two ranking from the same distribution compared to one ranking from this distribution, where do we have more noise?
No, but even so, the noise here is the theta parameter. So the idea is it's better to the noise here is the ranking. So the ranking as theta grows to infinity is going to become more stable. So it's actually going to converge. That's what they say the noise is. So they say even though it's going to become an expectation better,
No, I don't understand. So when you say WAA is just two copies of two A ranking or one A ranking. This is
That's the question. Yeah, that's.
because
you also confuse me now. I'm not.
Yeah,
I'm not
there is
position now.
no one can have this prisoner dilemma. It's interesting thing, or one can compare the. It can happen even for if we use some distribution twice. If we have two distributions, maybe it's better for both so that they can use both the first strategy and it's dominant to the second strategy, but still if they use it together, the first strategy, the expectation is worse for both than if they use together the second strategy. This is one type of things. So there are several, and strangely they say something about Brai's paradox, which I don't see what is the connection with Brai's, how you so they say that what is the difference between Brai's and prisoner dilemma? So each of them try to choose something which is optimal for both cases, for both strategies of the others, but still they lose compared to. So the Brai's paradox is somehow like prisoner dilemma for for specific case of a road movement or what?
I mean, the prisoner's dilemma here would be that this is the equilibrium, but this is the social welfare.
No, the Brai's paradox is not about social welfare. The prisoner's dilemma. It's not only the society loses if they both use the dominant strategy, but they both lose when they use dominant strategy compared to if they use the second one.
Prisoner's dilemma is the same.
Sorry?
I mean, prisoner's dilemma is the same. When we talk society, we actually say that the sum of the two players. We don't
not even the sum of. There are stronger thing for prisoner dilemma. If they both change the strategy, both will win. Not only the society will win, but both will win.
Yeah, the same for Brai's. The same for Brai's.
The society is the sum of both. Yeah.
Yeah. But then if and the same for Brai's. But then we don't need. Why we speak here about social welfare instead of the interests of both players? Why we, if we want to have a paradox, we need to consider social welfare. This is what I don't get.
No, in the prisoner's dilemma, they're not better individually if they both change.
No, they better individually. The prisoner's dilemma, if I confess, if both confess, they get a big punishment. And if both do not confess, they give a smaller punishment. But confessing is better, is dominant strategy for each player. So if they both confess or both not confess, the social welfare, since it's symmetric, the social welfare is more or less the sum of the two identical welfares for each of them. And somehow it's also the case here. Why do we need to consider social welfare if we have a prisoner dilemma?
Yeah.
Yeah, okay, maybe we should all look at the paper and try to clean it for all this blah blah and understand what is the real statement. So no, it's interesting if we can somehow formally explain what makes two measurements better than one. It's not so paradoxical, but it's worth observation, worth observating. So this is. Yeah. Okay. So so thank you anyway for the. It's interesting to see what people are doing, and we will maybe understand something, especially if Sasha will explain in a short note what was in the paper. I don't know whether whether it's how
I have
probable.
to just
Yeah.
read something or maybe ask.
For your previous explanation, I have a question. By the way, did you say that in Vereshagin's proof you just should take 0 prime as x or not? It what reading your notes?
More or less, yeah.
Yeah. Okay. But this is another story.
Yeah.
So, are there any questions for? I'm sorry for this. So, are there any questions about today's talk or comments or something like this? In addition to all the politically incorrect comments made already.
Very nice.
Okay, then what are our plans for Sasha? What are your or Kolya or somehow? What are our plans for next time? Are they announced or not?
We don't have yet any plans for next time.
Should we stop recording?
We cannot stop recording because it's happening.
We cannot,
It's happening in University of Bordeaux. They record everything. Actually, each of us can make
there
a.
was a variant.
I might
don't know,
be able to
next time.
re-log in.
No, don't do this. No, nothing critical happens.
No, actually, if it is possible to stop recording some moment, I think it is useful because some participants could be shy and don't ask stupid questions or supposedly stupid questions when it is recorded.
But we all ask stupid questions.
You are not shy, we know that.
Okay, but no, it's another story. If Misha next time can do this, it's better, but not to start to re-log in because I don't know what will happen with this.
I technically, okay, I will try to do it.
Okay, just do. If we don't have any plans for next time, we can stop now and we can send something by
we can have vacancies till February. Holidays till February.
No, if there is some talk for the next time, it's still maybe not too late, but I don't know.
No, next time is okay. So do we have somebody to talk for the next time? I mean, next Monday.
Just I apologize in advance. Next Monday I cannot participate.
Okay, Andrei can't participate, so that's a good reason not to have a meeting.
Yeah, okay, but then maybe okay, then we'll if someone
But you
has
want to have something in January or not, or you want to wait for February then, like
why not?
Like
why don't we should have something in January?
Because students have exams in January, they can't attend.
But do we have really any students here?
Yes, we have.
And actually, usually we have more
least
students
two.
than today.
At least 3, actually.
Okay, so if